Greetings. We have built up some information in our previous video, and now we shall continue with the rest of the combustion problem here. As for combustion of any fuel, there are two limiting cases that we usually consider. The first limiting case is where Q equals 0. If Q equals 0, and that is the Q, that is the heat transferred from this control volume, if the Q is 0, all the energy that is released in combustion would be used to heat the products, and therefore the products would be very hot. This would be the maximum temperature products could have since no heat is lost. And that temperature is called adiabatic flame temperature. As you see, the adiabatic flame temperature is function of two parameters. First, the number of molecules in the products, and N2 has a large part in it. The larger the number of molecules, the lower the temperature, the adiabatic flame temperature for that combustion. It also is a function of the extra air that they add to the product. So here there are more number of molecules in the products, and therefore the temperature would be lower. If, but for the original combustion, for the ideal combustion, the number of molecules is less, and therefore there would be a higher adiabatic flame temperature. The other limiting point for the combustion is that the temperature of reactants is equal temperature of the product. It means the temperature of two sides are the same, which means all the energy produced through this combustion is in fact collected from the combustion, and therefore the products are returned to the original temperature of the reactants. And therefore, that heat which is collected is the maximum heat possible to collect, and that would be the heating value. That would be called heating value. Heating value. That is the heating value that is known. And there are two types of heating value. One is higher heating value, and the other is lower heating value. What's the difference between the two? You see, if we return our product's temperature to the reactant's temperature, as the reactants are usually at 25 degrees C, usually, if it is the case. Therefore, the water in the products could be liquid or vapor. If the water is vapor, we have lower heating value. So this lower heating value is when the water is vapor. But if water condenses, then its heat is released to the vapor or gas, to the other gases, and therefore more heat could be collected from the combustion, and therefore the term is higher heating value. So this is liquid water, and this is vapor. The choice of which one should be used depends on how we see the combustion and the application we have. for it. You see, quite often say in gas turbines, what we need is not a cold combustion product since they enter the turbine and higher temperature is desirable. So, in fact, a high heating value and liquid water in the products is irrelevant. Low heating value would be more relevant to the problem. But if there is, say, a boiler, then the boiler uh, is an external combustion equipment, and therefore air should lose its heat to water, and the more it loses, the better it is. So a higher heating value would be more appropriate as the ideal heat that we could collect from the combustion. So these are the two limiting points that we have for the heat that could be collected um, from the combustion. One is when heat is zero, and therefore the products would have maximum temperature. That's what we call adiabatic flame temperature. And the other one is when all heat is collected from the uh, products, and therefore the maximum heat is collected from the combustion, and that's what gives us high heating value or lower heating value. Now let's return to our table, and what we had here was different products, CO2, H2O, O2, and N2, and since we assumed that the product temperature is 2 to 50 energies of each of the uh, constituents, that is CO2, H2, O2, and N2 are values as they are shown here. H4298 are these values, and therefore the difference between these two rows would in fact be the enthalpies of the products. These would be the sensible enthalpies of the products. Sensible enthalpies of the constituents are zero. Now, the total enthalpies of and also the products may be calculated here. How have we calculated these values? Let's um, calculate them here. Now, as for reactants, uh, we should uh, write it sigma NiHi, and that for reactants would be 1 C2H4, and its enthalpy of formation is this value 52 to 80, so it is 1 times its enthalpy of formation, which is 52 to 80, plus its enthalpy, its sensible enthalpy, which is 0, so it is plus 0. That's what we have for uh, C2H4. For O2 and N2, their enthalpies of formation is 0, and the sensible enthalpies are also 0, and therefore we shouldn't write them any longer. And the total value for the enthalpy of reactants would be 52 to 80 kilojoule per kilomole. Now, as for products, it would be more informative to calculate the enthalpy of the product. So, what do we have? We have 2 moles of CO2, you see, starting with CO2, we have 2 moles of CO2, so there is a 2 times. Now, the enthalpy of each mole of CO2 consists of its enthalpy of formation, which is minus 393,520 plus its sensible enthalpy, which is the difference between these two. Okay, let me write it in this way. It is plus 115,984 minus 936,934. Okay, and that is the value. The difference between these two is 106. The difference between these two is 106, 620, and the sum of all these together, I mean, it's also multiplied by 2. The sum of all this together would be minus 573,800. Okay, so this is how we calculate the enthalpy of CO2 in the mixture. Now, the rest of the story is pretty simple. As for H2O, there are 2 moles of H2O, so it would be 2 times the enthalpy of formation, which is minus 241,820, okay, and plus the change of enthalpy, which is 95562 minus 9904, and the outcome is 85,658. And if you add these together and multiply it by 2, the outcome would be minus 312,324. So this term would be minus 312,324. And let's do the same for the other two terms, which would be pretty simple. It would be plus, as for O2, the enthalpy of formation is 0, so it would be zero point 0.6 times. It's only the enthalpy change due to the added heat, and that is 68,715 plus, as for N2, it is 13.54 times 65187, and the outcome is 37,736.98 kilojoule per kilomole. Could also add the outcome here, and see, this is exactly what we have calculated. This term is the sum of these three, and this term is the sum of this lot. And therefore, HE is 37476, HI is 5228. Now, we could also write the first law of thermodynamics for this combustion, and the first law of thermodynamics would be 0, since it is as you assume it to be steady state combustion. 0 equals whatever that enters our control volume minus whatever enthalpy that leaves our control volume plus Q per kilomole of fuel. Okay, so it's a steady state enters and it, but it's not Q dot, it's Q because we are all calculating everything for every kilomole that enters our control volume and every kilomole of fuel that enters control volume. And if we just add to it how many kilomoles per second enters, then that would be a rate value. And there is no work. So this is the equation for first law for this combustion, and just putting numbers to it. 0 equals 5 to 80 minus 3776 plus Q, and therefore Q equals minus 14,544 kilojoules per kilomole of fuel. You see, Q is negative, and that means that heat leaves our control volume. Once it leaves our control volume, that would mean that our products, our products in fact could be even warmer than 2 to 50 if no heat uh, had left our control volume. Then our products would have a temperature even higher than 2 to 50. So if we want to calculate the adiabatic flame temperature, we should try values more than 2 to 50 to 500 or other values to get to a condition that Q would be 0, and that would be our adiabatic flame temperature. If we wish, on the other hand, to calculate the heating value, what we had to do is to assume that product temperature is 298, and therefore all these values would be 0. If product temperature was 298, all these values would be 0, and therefore the heat that we could calculate from this equation was the heating value. And I shall continue with the rest of this combustion problem in the next video. Cheers.